It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Okay, welcome to the second part in the 2.2 section on equilibrium and yield. Hopefully you've already looked at the first one, looking at just the concept of what equilibrium is and calculating Kc values. I want to introduce you to this man here, this French chemist, Chatelier. Unfortunately for him, he never got to experience the wonderful goodness of South Australian Farmers Union Nice Coffee. However, despite that, he was still actually able to contribute to chemistry. So he came up with what's called the CHATELIER'S principle, which basically states that if the conditions of equilibrium are changed, then the system will respond to counteract that change in order to re-establish equilibrium. Okay, so it's very, very wordy. Basically, the easy way to remember this is that if the system, which is at equilibrium, has something that changes it or impacts on it, the system will shift to try and do the opposite of what you did. So if you increase the concentration of something in your equilibrium, it will try and shift to decrease that concentration. Right? If you increase the temperature, the equilibrium will shift to try and decrease that temperature, and that's basically what it's all about. Again, there is a YouTube video here which I'll just hover over for you guys if you don't have the PowerPoint. Okay, I suggest you have a look at that one. That is one that specifically looks at the Chatelier's principle and is going to go through a lot of these things about equilibrium that we're going to talk about in a little bit more depth than what I'm going to do quickly in this just overview of the PowerPoint. Okay, so first of all, some things, and there's a couple of things that impact on an equilibrium. So I'm going to go through and try and draw those for you and explain. Like I said, the videos show a fair bit in more depth than what I can do, but I'll try and do it quickly here. So I'll just hover over this video link for you while I go through and explain. So in terms of concentration, if the concentration of one of the species in a reaction is changed, the rest of the species change concentration to re-establish equilibrium. So like I said, it's basically the exact opposite of what you're doing. So if you increase the concentration of a reactant, alright, the equilibrium shifts to try and decrease that concentration. Okay, and it will do that by actually doing the reverse reaction, in this case doing the backwards reaction and using up reactants to form more products. So it's doing forward reaction, I should say, sorry, and that'll become pretty clear in a minute. So I've got this equation here, which is a nice one, and I've actually color-coded some things here. Okay, so I've got hydrogen gas plus iodine gas giving us hydrogen iodide. It's a 1:1:2 ratio. Take note of the colors. So the hydrogen is orange, the iodine is blue, and the hydrogen iodide is pink. Now, what happens if more iodine is added to the system which has established equilibrium? Okay, well, what we're going to try and do is we're actually going to try and draw this. If I can just find where my cursor is, there it is. Okay, so let's try and draw. So first of all, we're going to start off with the hydrogen, which is orange. So if we let's start off with the iodine, given that that is the one that is actually being added to the system. Now, unfortunately, in this drawing, I don't have a pink, so I'm going to go kind of with a purple, which would be kind of close. Okay, so we're looking at the hydrogen iodide over here. So here you can see this is concentration on this axis here. This is time along the bottom. Okay, what we've got is that we've established our equilibrium. The concentration of our reactants is not changing, which means the rate of the forward reaction is the same as the rate of the back reaction. So if we are increasing, or we add in some iodine into here, I don't know why I'm going purple, sorry. I think this is late at night, and I do know the reason why I'm having some issues. It's because I need some more iced coffee. So what we're going to do here is we're going to look at the iodine, sorry, because we're adding more iodine into the system. So if more iodine is added in, what happens is that the iodine concentration goes straight up. Alright, I'm drawing using a mouse, sorry, so it's not the greatest, but I'll try and do my best. So the iodine concentration goes straight up. Neither of these two change because all we've done is add iodine in. Now the equilibrium shifts to try and decrease this iodine. Okay, and the way it does that is it's going to use up the iodine by reacting with hydrogen to form hydrogen iodide. So what's going to happen is that the concentration of the iodide, as it is reacted with hydrogen, is going to decrease. Okay, now because it is reacting with the hydrogen gas, the hydrogen is also going to decrease. Now, hopefully what you can see with my excellent art skills is that the change in value from here to here, alright, is actually the exact same value change we've got from here to here. Now hopefully you'll be able to understand this, because for every 1 mole of hydrogen that reacts, we use up 1 mole of iodine. So these two are going to decrease in concentration by the same amount, because we have to use the same amount as they react together. Hopefully, therefore, what you'll be able to then work out is that the hydrogen iodide here, the purple one, is going to increase by double that amount, because the ratio is 1 to 1 to 2. So this is actually going to increase as we use up our hydrogen and iodine, and it's going to go up, oh, there's my awesome drawings, look at that, by 2x values. Okay. Alright, I've got 5-year-olds, I reckon they draw better than I do on a computer already. That's how wonderful it is. Alright, x here, that goes up by x, and this one here will, goes down by x, and this one goes down by x as well. Okay. Now, we get to, oh, look at that, I don't know what that is, but that is not an x, sorry, but we're going to go with it. Alright, we get to the point where the concentration of all 3 of these are now constant. So at this point here, where the slope is 0 again, we've established our new equilibrium. Okay, and so now our system has shifted to counteract the change by decreasing the concentration of iodine that we added in. It did this by shifting to the left, or favouring the back reaction. Okay, so when we're talking about what the equilibrium actually does, we talk about which way it shifts, right or left. Okay, in this case it shifted to the left. Let me restart that, sorry. So what we're talking about here is our equilibrium has shifted, and in this case it shifted to the right, okay, because it wants to decrease the concentration of iodine. So we shift it over to the right, over here, to decrease this iodine concentration, and the concentration of the hydrogen iodine goes up. The hydrogen and iodine goes down by the same ratio until we establish our new equilibrium. Alright, what I've gone through here on this slide is just exactly what I've spoken about there, so you have an opportunity to read through that if you want, but I want to move on to the next one. So pressure is another one that we can look at, and I'll just again hover over this video so you can have a look for those who want to actually go and check out that one as well. So with pressure, what you've got to understand is that solids and liquids cannot be compressed. Okay, only gases can. So a pressure change is only going to influence an equilibrium that involves gaseous molecules. If there's no gaseous molecules, no pressure change will actually impact on it. Now, what you've got to understand is the characteristic of gases, where they try to expand to take up as much space as possible. Okay, so if you think about this when you breathe out, okay, on a cold day and you see sort of your water vapor that's coming out of your mouth, you'll notice that it doesn't just hang in front of your mouth, it just goes and takes up all the space. Same thing about smells, for example. Smells are a really good example. If you have a smell in a room, over time that smell disappears because the gases that are responsible for the smell are dispersing and taking up as much room as they can, and so the concentration of them decreases in that volume of space. So when you increase the pressure of a system, what you're doing is you're taking all your particles which are in this space, and you are taking the same number of particles and you are squishing them into a smaller space. Okay, so what you're doing is you are increasing the concentration of your particles. Okay, now gases don't like that, because they want to try and take up as much space as possible. You've increased the concentration, so what the system wants to try and do is decrease that concentration. Okay, and it does that by favouring the side which has the least number of gaseous moles. So if you take 20 moles in here and you compress it down, it's going to try to decrease the number of moles. It's going to try and reduce those 20 moles you've got down to, say, 10, and then the pressure isn't going to be as great, and it's offset what you've done. Likewise, if you actually increase the pressure, okay, what happens is the gases have got more room, they want to take up more room, so there's more reactions that occur to produce more moles, and that's the opposite of what you're trying to, of the impact you put upon the equilibrium system. Okay, so a decrease in pressure favours the side with the greatest number of moles, and an increase in pressure favours the side with the least number of moles. So if we go to this equation here, the Haber process, what you do is you have a look at how many moles you've got on each side. So here we've got a 1 and we've got a 3. So overall on this side we have 4 moles. Here we've got 2. So we've got, oh, that's a brilliant 2. Here we've got 4 moles in equilibrium with 2 moles. So clearly this side has the least number of moles. Okay, So if we increase the pressure, it's going to favour this side. Okay, here we've got 3 moles in equilibrium with 2, and so a decrease in pressure is going to favour the side with the most number of moles, which is 3, so it's going to favour the left reaction. It's going to shift to the left. Here we've got 2 moles, which is 1 and 1 there, in equilibrium with 2 moles, so pressure is not going to have an impact upon this at all. Now what we should say about the benefit of increasing the pressure, as I said, if you remember, is that increasing the pressure increases the concentration. And if you increase the concentration, according to the collision theory, you increase the rate of a reaction. So quite often in industrial chemistry we will increase the pressure in order to make the reaction occur faster. Okay, and I've just explained this here again about increasing the concentration if we increase the pressure. So that's quite important in terms of industrial chemistry, because it does give you a faster rate of reaction, because these particles here are going to collide much more frequently than these ones, so you're going to have a much higher chance of a successful collision per unit time here than you would up here. So if we go to this reaction, nitrogen dioxide, which is a brown gas forming N2O4, which is colourless. Alright, if we increase the pressure of the system, what happens? Okay, well, first thing we need to remember is that increasing the pressure of the system increases the concentration. So again, I'm going to use my purple here to represent nitrogen. It's the N2O4, I should say. So we're increasing the pressure, so straight away concentration increases. Okay, same for the nitrogen dioxide up here in blue, so that concentration increases as well. So at this point here, if you see every species on the graph increase or decrease in concentration immediately, it means a temperature change. Notice when we were doing, it means a pressure change. Notice when we were doing one for concentration, only one of them changed. When you get to temperature, which is the next one, you'll see that none of them changed. So you can actually tell from the graph what's happened to it. Now, up here, we've got 2 moles in equilibrium with 1 mole. So if we increase the pressure in the system, it's going to favour the side with the least number of moles. So that means the equilibrium is going to shift to the right or favour the products, because there's less moles here, and so going to here will decrease the pressure in the system, which is counteracting what we did. So that means our NO2 is going to be used up. Okay? And now, using the mole ratio 2, that's going to go down by a value of 2x. So we don't exactly know what it is, but it's just going down by a value of 2. Now, our N2O4 is going to go up. Okay, it's going to go up by a value of, let's keep going up, sorry, it's supposed to be a straight line from there, but it's going to be going up by a value of 1x. Oh, my x's tonight are absolutely woeful, sorry, so I do apologise for that. Okay, so I am actually going to get rid of that because I should not be teaching with something that looks like that. Okay, so that goes up by a value of 1x. Alright, so we're keeping the mole ratio here. We get to this new point where the concentrations of them are stable. So there's our new equilibrium. Seriously, until you guys have tried writing with a mouse, you can't judge me. Alright, you get to this point where the concentrations are equal, so we've established our new equilibrium. The system has counteracted the increase in pressure by favouring the side with the least number of moles. Okay, so I've just gone through, explained all of that again. Okay, final one I want to look at is temperature changes. So an increase in temperature favours the endothermic reaction. Now you've got to think about that pretty logically. Endothermic reaction is one where energy enters the system. If you're increasing the temperature, there's more energy you can put into it, so it's going to favour that system. Likewise, an exothermic reaction tries to give out energy. Alright, if the surroundings are hot, it's much harder to give out energy to heat up those surroundings, so it's not going to be favoured. Alright, so increasing the temperature does change the Kc value. So what we need to understand is that for pressure and concentration, the Kc value stays the same. The equilibrium shifts to counteract the change, and it re-establishes a Kc value which is the same. However, for temperature, that's not the case. Okay, and you'll see that when we draw the graphs. Okay, of that, we don't have that increase in concentration or decrease in concentration of a species at the beginning, which will offset change in equilibrium that we have. Here all we're going to do is change the concentration, which is going to change Kc. Now, remember back to the collision theory, that an increase in the temperature changes the Kc value because particles move faster, have more collisions per unit time, and more particles have energy greater than or equal to activation energy. Okay, so I'm going to go back to this reaction that we just had, the NO2 and N2O4. Now, this time here, you need to have a bit of an understanding about enthalpy values, I should say, and a negative enthalpy value. So and here we've got negative 57 kilojoules. That tells us that it is an exothermic reaction. So back here, sorry, I didn't actually hover over the video, but this will go through a little bit more in terms of reminding you about enthalpy signs and values, okay, if you need to do that. So here we've got negative 57, so that this forward reaction is exothermic. So if we increase the temperature, okay, increase in temperature favours the endothermic reaction. So in this case, the increase in temperature is going to favour the back reaction. Okay, so what that means is we don't have any concentration changes, but what that means is that our N2O4 is going to be used up. Okay, so this is going to decrease in concentration, okay, by 1x, simply because the back reaction uses up energy, okay, and so it's going to offset that increase of energy that we're putting in. So the NO2, the nitrogen dioxide, okay, is going to go up in concentration, and it's going to go up by 2x amount, again keeping in mind the mole ratio of the equation. Okay, and so the back reaction is favoured, the concentration of NO2 up here goes up, concentration of N2O4 decreases until we get to a point where we again have re-established our equilibrium. Okay, so like I said, we don't have any concentration changes straight away up or down like we did with pressure or concentration. When we impact it, all we do is we change the concentration, which is going to impact our Kc value. Alright, so this is just explaining what I've done. Equilibrium shifting to the left, favouring the back reaction, which is endothermic, and we get our change. Final thing you can look at is a catalyst. Now, got to remember that definition of a catalyst from rate of reaction. Catalyst increases the provides an alternative reaction pathway with a lower activation energy and helps to line particles up with the correct orientation. So what it's going to do is it's just going to get the reactants and products to reach equilibrium faster. It doesn't actually impact on the concentration of either of them though, and so we don't have to draw a graph because it just allows equilibrium to be obtained faster. So you can show that in a graph. If this is the normal rate of the decrease in reactants and this is the rate of increase of the products, all that's going to happen is that the concentration of your products is going to be obtained faster than if you did it without a catalyst. Okay, and that's important for when we go on to the next part of this topic, which is all about optimizing production. So I know I've gone through these factors that influence equilibrium reasonably quickly. Out of this video, you need to make sure you understand a concept of the CHATELIER'S principle, where an equilibrium will shift to counteract a change that you bring into it. There are three main changes, which is changes in concentration, changes in pressure, and changes in temperature. And you need to understand how an equilibrium is affected by each of those changes and be able to draw those graphs similar to what I've done today. So, as I said, have a look at the individual YouTube videos. There's one for each of concentration, temperature, and pressure if you need to have a look. And as always, if you've got any questions, just ask. Alright, thanks guys.